Hey there, and welcome back. Today, we're diving headfirst into something that, well, feels like it's rewritten the rules right before our eyes. Generative AI.
hmm
You've seen it. It's the tech behind all that surprisingly creative stuff popping up everywhere, making art, drafting emails, maybe even helping write code.
And to guide us through this, we've got some really insightful source material. It's a comprehensive overview that walks us through the fundamental concepts and just how fast this technology has evolved.
Absolutely. So our mission for this deep dive is, well, pretty clear. Cut through the noise, try to understand what generative AI really is,
Yeah.
get a peek at how it works its magic, kind of under the hood, and see where this whole roller coaster ride seems to be heading.
hmm
We're using these sources as our map, basically.
Right. The aim is to equip you with the core knowledge, pull out those crucial insights, and, maybe save you endless scrolling through headlines. Let's figure out what really matters here.
Okay, let's unpack this then. What is generative AI, like at its core? The sources tell us it's essentially deep learning models designed to generate high-quality content.
Right. Things like text, images, even music.
And it's all based on the massive amounts of data they were trained on.
Think of it as learning the underlying patterns, the structure of data, and then being able to produce something brand new that fits those patterns. But it's new.
And the sources make a really interesting point right away. AI has had these hype cycles before, right? We've seen this move.
Oh, yeah, definitely.
But something about the release of ChatGPT felt, I don't know, profoundly different. It felt like a genuine turning point, even for people who thought they knew what AI could do. Suddenly, you had models writing poems. And not just any poems, apparently love poems in the form of Yelp reviews.
That example always gets me. It's so specific.
Right. Or telling surprisingly decent jokes, churning out essays, song lyrics in the style of, I don't know, Nick Cave or something. It was this sudden, tangible demonstration of creative potential that anyone could just play with.
And that moment really highlighted a significant shift. The last big public splash for generative AI was often in computer vision, like filters that change your appearance or style on your phone.
Right, selfie filters.
Exactly. This current explosion is really powered by major breakthroughs in natural language processing, particularly with what we call large language models, or LLMs.
But it's not just language, which is fascinating. The sources note these models are learning the grammar, if you will, of all sorts of other data types, too.
Totally. Software code, the structure of molecules, images, complex data sets.
It's learning the rules.
Pretty much. And that's where the applications move well beyond just generating fun text or images. The source material points to research labs, like IBM's, using these models to actually speed up writing software code.
Which developers probably love.
I imagine so. Or to discover entirely new molecules that could become medicines, or even build highly reliable chatbots specifically trained only on a company's internal data so they don't just make stuff up.
Avoiding the hallucinations, yeah. Oh, and the synthetic data piece is huge. Creating realistic but fake data for training other AI models or, to use when privacy is a major concern. That's a really practical, maybe less glamorous, but high-impact use case mentioned.
Exactly. It shows this isn't just about novelty. It's a fundamental shift in how we can interact with and generate information across many, many fields.
So that's the what and the why now. But the big question is how. How do these things actually work? Let's peer under the hood a bit. The sources lay this out pretty nicely.
Okay, so at a high level, here's the kind of magic trick. The model takes raw data, could be a sentence, an image, whatever, and it learns to compress it. It makes a simplified, abstract representation.
Like summarizing a complex document into its core ideas.
Yeah, kind of like that. Then, when you ask it to generate something, it samples from that compressed idea space to create something new. It's statistically likely based on the original data, similar in style, but importantly, not a direct copy.
Okay, like getting the gist and then riffing on it. Got it. And the sources remind us that generative models actually existed in statistics before deep learning, right? For numbers and simpler stuff. But deep learning is what cracked it open for complex things like recognizing speech or understanding images.
Precisely. And pivotal early breakthrough they highlight was variational autoencoders, VAEs, back in 2013. Autoencoders already existed to compress data and then reconstruct it.
Like zipping and unzipping a file.
Exactly. VAEs added this crucial element, the ability to introduce variation when reconstructing.
Ah, so the generative part really starts kicking off here. And they even quote Akash Srivastava saying, VAEs opened the floodgates. Like much of what we see today started with that basic idea.
That's right. The core idea is this encoder-decoder structure. The encoder takes the input, turns it into that compressed representation, making similar pieces of data cluster together in this abstract space. Then the decoder takes a point from that space and expands it back out into a new output, trying to keep the key features. This architecture is fundamental to VAEs, and it also forms the basis for modern large language models.
Got it. Compress, then expand with variation. Simple enough concept, complex execution, I bet.
Right.
And then came the absolute game changer in 2017, right? The sources call it a landmark paper.
Yes, the Transformers. From that famously titled paper, Attention is All You Need.
That title alone makes you lean in. What was so revolutionary about it?
Well, pretty much everything. Previous language models were like reading a sentence word by word sequentially. Very slow.
One after the other.
Right. Transformers processed words all at once, in parallel. This made training dramatically faster on huge data sets.
Okay, so speed was a huge factor.
That's
Got it.
huge. But maybe more importantly, they learned the relationships between words, even across long distances in a sentence. They understood the context. This attention mechanism allowed them to sort of weigh which words were important to each other, giving them a much deeper understanding of meaning and allowing them to figure out ambiguities like, does bank mean a riverbank or a financial institution?
Yeah.
Context tells you.
That starts to sound less like just statistics and more like something actually grasping meaning. And this led to another massive shift. Pre-training on vast amounts of unlabeled data.
This is where things really changed the game. Before Transformers, if you wanted a model to, say, classify text or answer questions, you had to gather and label data specifically for that one task. Very laborious.
Right, painstaking work.
With Transformers, you train a huge model on pretty much the entire internet, unlabeled, just raw text. And it learns a general understanding of language structure, facts, context, all that stuff.
Okay.
Then you only need a small amount of labeled data to fine-tune that massive model for many different tasks.
So you train one giant brain and give it little bits of specific job training afterwards?
Exactly. That's why they're called foundation models. As Akash Srivastava puts it in the source, instead of needing mountains of labeled data for every little thing, you feed these foundation models massive unlabeled data so they learn these general, transferable representations of knowledge. It's much more efficient.
Okay, so the Transformer family is pretty big now, and the sources break them down based on their architecture.
They do. First, there are encoder-only models, like BERT. These are fantastic at understanding existing text, but not necessarily generating lots of new text from scratch.
Okay, so for things like figuring out the sentiment of a review, positive or negative, or pulling specific info out of a long document?
Precisely. They power search engines, analyze customer feedback, and are used in chatbots like IBM's Watson Assistant for understanding what the user is asking. There's a cool example in the source about IBM using an encoder-only model to mine millions of Earth science journals for NASA.
Wow.
Pulling out key insights automatically.
Mining journals with AI. That really does sound pretty sci-fi.
Yeah.
Okay, what's the next branch on the family tree then?
Then you have decoder-only models, like the famous GPT family, ChatGPT being the most well-known example. These are trained primarily to predict the next word in a sequence. They don't really have that separate encoder step that processes the input in the same way.
And these are the monsters, right? The sources list off the sizes. GPT-3 at 175 billion parameters, Paul at 540 billion, Bloom at 176 billion, parameters being like roughly the number of knobs the model can tune during learning. That's just an incomprehensible number.
Truly staggering, and that sheer scale is what gives them that uncanny ability to generate coherent dialogue, write long essays, produce creative text. The stuff that floored everyone with models like ChatGPT, they're built to generate word by word what should plausibly come next.
Makes perfect sense for why they excel at conversation and writing them. Okay, and the last type.
Finally, there are encoder-decoder models like Google's T5. These combine features of both.
Sort of the best of both worlds.
In many ways, yeah. They can do a wide range of tasks, both understanding input and generating output. And the sources note they tend to be more compact than the giant decoder-only models,
Ah, well,
which makes them faster and cheaper to tune and run for specific tasks,
yeah,
which is really important for practical applications where efficiency matters, budgets and speed.
definitely. So we have these incredibly powerful models trained on just unimaginable amounts of data.
Yeah.
But the sources mention that humans still play a really crucial role in making them actually useful and, importantly, safe. Supervised learning, the old way, is kind of making a comeback.
It is, yeah, but in a new form. Developers are using targeted human supervision to shape how these powerful models interact with us, to guide them.
How do they actually do that? What are the techniques?
Well, one key method is instruction tuning, mentioned with models like Google's Fallion. Instead of just training the model to predict statistically likely text, they show it examples of specific instructions paired with correct responses.
Like question-answer pairs.
Exactly. Things like, what's the capital of France? And they answer Paris, or sort this list alphabetically, and then showing the sorted list. This teaches the model to follow commands and provide helpful, relevant answers, not just spit out plausible-sounding text.
Ah, so it's training the model to be obedient and helpful, not just fluent. Makes sense.
Precisely. And then there's prompt engineering, which is more about how we interact with an existing model. It's the art of crafting the input text, the prompt, to get the specific output you want from a foundation model.
Right.
You can ask these versatile models to do something they weren't explicitly trained for, often just by describing the task clearly in the prompt. Sometimes you need no examples in the prompt. That's zero-shot learning. Sometimes just one or a few examples helps guide it. That's one-shot or few-shot learning.
That sounds incredibly powerful and efficient. Like you don't need a huge data set for every new little thing you want the model to do. Just ask it nicely.
Dramatically less time and data compared to building a custom model from scratch. But the sources are honest about the downsides here, too. Prompt engineering can be fiddly.
Fiddly, I believe it.
The models are really sensitive to tiny changes in phrasing or formatting in the prompt, and what works perfectly for one model might not work at all for another. It's not always reliable or transferable.
Fiddly AI.
Yeah.
Sounds about right for cutting-edge tech. Okay, what about getting these big models to work with the company's private, sensitive data? Fine-tuning a giant model like GPT-3 on proprietary information sounds, well, expensive and maybe risky.
It absolutely is. Very computationally expensive, and you have data privacy concerns. So newer methods have emerged, like prompt tuning and adapters. These are sometimes called parameter-efficient methods.
Okay, prompt tuning sounds like prompt engineering, but you said it's different. How so?
It's a bit more technical, yeah. Instead of just the user writing a clever text prompt, these methods actually learn a small set of new parameters specifically for your task or data. Think of them like little add-on modules. These small learned parameters are then inserted into the main foundation model, which is kept frozen. Its original billions of parameters aren't changed. These little add-ons subtly redirect the massive model's behavior to follow your specific data or instructions.
Oh, I see. So you're not tweaking the whole giant brain. You're just giving it a specialized attachment or lens that focuses its power on your specific problem using only your data. That's really clever.
It really is. As David Cox from MIT IBM is quoted saying in the source, it allows users to have their cake and eat it too.
Oh, I like that.
You get to leverage the immense power of a huge pre-trained model while keeping your specific data separate and only needing to train and manage a tiny set of parameters. Much more practical.
Have their cake and eat it too with AI. Love that analogy. Okay, and there's one more big piece to this puzzle of shaping AI behavior. Alignment, right, especially RLHF.
Yes. And finally, a huge part of why models like ChatGPT feel so natural to talk to is alignment, particularly reinforcement learning from human feedback, or RLHF. OpenAI really popularized this.
Right, how does RLHF actually work? I hear that term thrown around constantly.
It's a multi-step process, but the core idea is this. The model generates several potential responses to a prompt. Then humans act as raters. They look at the responses and score them, or rank them, based on criteria like helpfulness, truthfulness, harmlessness, lack of bias, things like that.
Okay, humans judging the AI's homework.
Kind of. They even train a separate reward model to predict these human preferences, to learn what humans consider a good response. Then, using reinforcement learning, which is like training a robot through trial and error with rewards, the main AI model is adjusted to produce responses that are more likely to get those high human scores or high scores from the reward model.
So it's literally learning to be the kind of conversational partner we prefer based on our direct feedback loops. That explains why ChatGPT felt like such a leap in just interaction quality.
It absolutely does. It results in what the sources describe as high-quality conversational text that aligns much better with human expectations and values. It's less likely to just ramble or say unhelpful things.
Okay, fascinating stuff on how they work and how we shape them. So what's happening right now, like on the cutting edge? Where is this all going next?
Well, until very, very recently, the dominant mantra was just scale. Bigger is better.
Right.
The sources highlight that training larger models on more data consistently led to better performance across the board. Researchers even developed these things called scaling laws.
Scaling the laws.
Yeah, mathematical relationships that could predict how much better a model would get just by making it bigger and feeding it more data before they even spent the massive computing power and money to train it.
So the approach was literally just keep adding more layers, more parameters, more data, and performance will predictably improve.
Pretty much. And a major driver for this was something the sources call emergent capabilities. These are skills that seem to just appear almost magically when a model reaches a certain massive size.
Appear, like out of nowhere.
Sort of. Things like glimmers of logical reasoning, or following complex multi-step instructions better, or even basic arithmetic abilities they weren't explicitly trained for, but seemed to emerge from the sheer scale. It was like hitting a critical mass, unlocked new potential, pushing labs to train ever larger models.
Capabilities just emerging from scale. That still feels a bit like science fiction. But you said until very recently. Is that changing now?
It is. There's recent pretty compelling evidence that's starting to challenge that bigger is always better idea. Several research groups are finding that smaller models, when trained on more specific, high-quality, domain-focused data, can actually outperform much larger general-purpose models on tasks within that specific domain.
Like having a specialist versus a generalist again.
Exactly that analogy. The sources give the example of Stanford's PubMed GPT. It's a relatively small model, like 2.75 billion parameters, tiny compared to GPT-3's 175 billion.
Tiny, yeah, relatively speaking.
Yeah. But it was trained specifically on biomedical literature, like medical journals and abstracts. And it significantly outperformed a general model of the same size on medical question-answering tasks. David Cox uses that great analogy again. When you have a specific medical question, you ask a domain expert, right? Not just the single smartest person you know, who knows a little bit about everything.
That makes perfect intuitive sense. And I imagine smaller models have some pretty big practical upsides, too.
Huge ones. The sources point out they're significantly cheaper and less carbon intensive to train and run. That's massive for accessibility and, the environment.
Cheaper, greener, and potentially better for specific jobs. That sounds like a major potential shift in the field.
It really feels like it could be. And complementing this is another emerging trend the sources cover, model distillation.
Distillation.
Yeah. The sources highlight the Stanford Alpaca project as a key example. They aim to basically distill the capabilities of a large, powerful model, GPT 3.5 in this case, into a much smaller, more efficient one.
Distill, like extracting the essence, the good stuff.
Yeah.
How do you do that?
Precisely. They use the big model, GPT 3.5, to generate thousands and thousands of instruction response pairs, basically, having the big AI follow instructions and provide high-quality answers. Then they use that AI-generated data to instruction tune the much smaller Alpaca model, only 7 billion parameters.
Oh, hold on. They used a big AI to generate the training data to teach a smaller AI.
Yeah.
That's like AI teaching AI. My brain is definitely doing some processing right now.
Agrees. It is. It's a wild concept. And the result was this small alpaca model that exhibited surprisingly similar conversational abilities and instruction following skills to the much larger ChatGPT, despite being way smaller and cheaper to run.
That's truly mind-bending.
And since Alpaca, a whole herd of similar models, they mentioned Vicuna and Dolly, have popped up, often trained using variations of this distillation technique.
Wow. And David Cox's point in the sources about Alpaca really hits home then. It calls into question whether training these absolute massive models on enormous data sets is the only way, or even the best way, to achieve these complex emergent capabilities.
Right. Maybe the capabilities aren't solely tied to parameter count, but also to the quality and nature of the training data, even if that data is generated by another AI. And the sources note some follow-up projects, like Dolly 2, are even trying to crowdsource high-quality instruction response data directly from humans, skipping the AI-generated step altogether.
So maybe the future isn't just about this relentless chase for ever larger models, but about smarter, more targeted ways to train smaller, more focused, and maybe more efficient ones.
That's exactly the implication of this recent work. It suggests we might be heading into an era where more compact, efficient models are actually powerful enough for a wide range of practical uses, potentially making advanced AI much more accessible and specialized.
Okay, so immense potential, rapid innovation, fascinating shifts in direction. But the sources are careful to balance that excitement with the necessary caveats. It's not all seamless creativity and problem solving. There are significant risks involved here.
Absolutely. You have to be aware of the downsides. The potential is huge, but deploying these models carries real risks. The sources list legal, financial, and certainly reputational risks.
And what are the common pitfalls they highlight?
Well, one of the most talked about is hallucinations. That's the term for when the model outputs information that sounds completely confident, authoritative, grammatically perfect, and factually correct, but is actually pure invention, made up.
Hallucination is such a perfect, slightly unsettling word for it. It truly sounds like it's just confidently making stuff up sometimes.
It really does. And related to that, of course, there's the ongoing risk of models producing objectionable or biased content. This often stems directly from biases present in the vast, often unfiltered data sets they were trained on, garbage in, garbage out to some extent.
Right, if the training data reflects societal biases, the model will likely learn and unfortunately amplify them. That makes sense.
And finally, there are significant privacy and intellectual property challenges. Because these models train on enormous amounts of data scraped from the internet, books, code repositories, all sorts of places.
Yeah.
They can inadvertently memorize and then later reproduce personal information, sensitive data, or copyrighted material that was in their training set.
Which creates real headaches for compliance, legal teams, creators, pretty much everyone.
Exactly. It's a really complex challenge to figure out how to ensure these models respect privacy and IP rights while still allowing them to learn from the vast amount of human knowledge available.
Wow. Okay. This deep dive has really covered a lot of ground. From defining generative AI and marking ChatGPT as that kind of public turning point through the technical foundations like VAEs and those revolutionary transformers.
Unpacking how those transformer architectures come in different flavors, encoder only, encoder decoder, and how human feedback, instruction tuning, RLHF, and those clever parameter efficient tuning methods really shape their behavior.
And finally, looking at the cutting edge, where
Right.
that relentless pursuit of just massive scale is maybe being questioned by the surprising power of smaller, specialized models and this intriguing idea of AI teaching AI through distillation. That's a lot.
It is a lot, but understanding these core pieces, the types of models, the key architectural shifts like attention, the different training and tuning techniques, it really is fundamental if you want to make sense of how quickly this field is evolving and where it might go.
It truly is. It's definitely a complex space, but when you break it down like this, using the sources, the underlying concepts are actually quite understandable, and the pace of development is just breathtaking.
It makes you wonder about the future, doesn't it? Where does this all lead?
It really does, especially
Mm.
thinking about that point the sources raise regarding smaller, specialized models and distillation. Are we necessarily heading towards a future dominated by just a few enormous monolithic AI models that try to know everything? Or, or are we potentially moving towards a world filled with many specialized AI experts? Smaller, more efficient models, each finely tuned for specific tasks, specific domains.
A whole ecosystem of AI specialists, maybe.
Exactly. And how might that totally change how we interact with AI every single day? Something to think about.
A profound question raised directly by these recent trends in the research. Definitely something to keep an eye on.
Absolutely. Well, thank you for joining us for this deep dive into the fascinating, fast-moving world of generative AI.